I'm Kotaro Kinoshita. I work for Fujitsu. Today I'm going to talk about the challenges of vectorizing strided axis. Vectorization is generally expected to improve performance. However, we found that the performance degradation in some cases of vectorizing strided axis. This talk focuses on one such case. For example, in the test case shown on this slide, SV vectorized version actually performs worse than the scalar version. We found this performance degradation is caused by inefficient code generation for strided axis, and we opened an issue for this. In this talk, we will discuss this issue and its improvement status. While this talk focuses on ARC64 SVE, we believe this issue may be relevant to other architectures as well. One of the problems with the code generated by the current LLVM vectorization is its inefficient address calculation. With SVE, strided axis requires the use of gather instructions. In the currently vectorized code, the addresses for the gather operation are updated inside a loop using vector instructions. As you can see in the example on this slide, the vector register Z1 is updated in every iteration. But if we identify the patterns as a strided axis, we can generate efficient instructions like these. The value of vector register is initialized outside the loop, and then inside the loop, the base is updated using scalar instructions. In the example on the slide, you can see that the base x1 is updated in every iteration. This code is more efficient because it requires fewer resources for address calculation. Next, I'll explain the improvement status for this issue. Fortunately, a patch had already been contributed for RISC-V, which has dedicated strided load store instructions. This patch detects the stride axis patterns in loop vectorize and assigns it a strided load recipe. However, ARC64 doesn't have these dedicated strided load store instructions. So we couldn't use the recipe directly. So our contribution was to create a patch that legalizes the recipe for ARC64. This patch replaces the recipe with the efficient sequence of instructions we saw on previous slide. In fact, for the test case from the introduction, our patch improves performance by 37% compared to current vectorization. Finally, I'd like to briefly touch on some other issues of vectorizing strided axis. First one is loops with a variable stride width are not being vectorized effectively. This is related to loop multi-versioning. Only the version where stride is 1 gets vectorized, while the other case remains scalar. Another one is the in-the-bar simplify when widening the index of strided axis to 64-bit can potentially double the number of memory access instructions. We've listed the related issue number on this slide. That's all. Thank you very much.